let's say someone gives you this equation and says, hey, is it balanced? Well, what you do is you go element by element and just check. So what elements are in this? Well, there's a hydrogen, right? So there's at least hydrogen. Phosphorus, oxygen, magnesium. Okay, so we got, I think that's all of them. So I'm just writing out all the elements. And by the way, I didn't come up with this. I was very sloppy about this, but students showed me how to do this when I was tutoring them. Yeah, I was tutoring them. So yeah, a lot of them write a line down the arrow. Like they just write a line there, and then they just write like HPOMG below the equation. And it makes things a lot more orderly. I swear, like the more like little tricks you can do to organize your work, the less weird mistakes you're going to make that have nothing to do with how well you know the material. Let's go through element by element and see how many H's, or sorry, molecule by molecule, and see how many H's they give us. So for phosphoric acid, there are 2 times 3 H's, so that's like 6. And for magnesium hydroxide, each magnesium hydroxide has 2 H's because it has 2 hydroxides. And there are 3 of them, so that means that there's 3 times 1 for the H times 2. That's 6. So 6 plus 6 is 12. In the reactant side, for hydrogen, water is the only molecule that has it. So if I look at water, 2 H's per each water. There are 6 of them. 2 times 6, 12. So the H's are balanced. There's 12 on each side. 12 in the reactants, 12. Wow. That's a big mistake, everybody. You didn't help me out. Yeah, I mixed them up. Yes, that's how you do it. You make sure that like the products and the reactants have the same number of each element. Phosphoric acid. Each phosphoric acid has 4 oxygens, right? That's what the 4 means after the O. So there are 2 of them, 2 phosphoric acids. So 2 times 4, that's like 8. And magnesium hydroxide, how many O's does it have? How many oxygens? Well, each hydroxide has 1. There's 2 per magnesium hydroxide. And there are 3 magnesium hydroxide molecules, or compounds, in this reaction. So we add everything up. That's 8 plus 6, that's 14. Okay, for oxygens in the products, we have 6 H2Os, so that's 6 times 1 oxygen per water, that's 6. And in magnesium phosphate, we have 2 phosphates with 4 oxygens each, so that's 8. 4 times 2 is 8. And there's only 1 equivalent of magnesium phosphate listed in this reaction. So 6 plus 8, that's 14. So this whole thing is balanced. Each and every element has the same number of atoms in the reactants as the products. I hope this is making a lot of sense. What's nice about this method, in addition to the fact that it's kind of like, you know, resistant to my making a mess, like with this table, and you draw a line down the arrow, and then you separate reactants and products, and you do the multiplication, you add it up. You have to get it wrong twice to agree with the wrong answer, right? So like, the reason why I didn't make any mistakes on this, is except for labeling, is because for me to have made a mistake and to have like passed it off as being correct, I would have had to have gotten like 11 over here and then 11 over here again. That's pretty unlikely. The format helps me do it. So if you calculate that there's like O's on one side and they're not the same as the O's on the other side, either the reaction isn't balanced or you didn't calculate them correctly. Here's another example. This is photosynthesis. We can balance these together. So let's start with the methane. How many carbons are in methane? 1, right. There's also just 1 in CO2. So from a carbon perspective, this is currently balanced. How many hydrogens are in methane?
4.
Right. There are 4 hydrogens in methane. How many hydrogens are there in water? 2. Right. There's 2. So I'd have to put a 2 in front of this water to make it balanced. So then at that point, I would have 4 hydrogens on either side. I'm curious if this is where they're going. Yeah. Oh, OK. So you're going to have to get rid of 1s at the end. How many O's are on the product side?
2 currently, but that needs to be 1.
Right, O's, not H's, O's. So there's no subscript there behind the O's, so that means there's just 1 per molecule. There are 2 molecules of it, so that means there's 2. How many O's are in O2? OK. How many O's are in CO2?
2.
Right. So in the product side, I have a right-left problem, so you guys are going to have to bear with me on that. Thank you for your patience. Yes, there are 4 O's total here, 2 for each kind of molecule. Right? 2 here and 2 from the 2 waters. So that means we have to put a 2 in front of the O2. Right? This is very anticlimactic. You figured this out about 5 minutes ago. But yes, it'll be a 2 in front of the O2. And now everything's balanced. There's actually 4 O's on this side, and there's 4 here. Why? 1 times 2 is 2. 2 times 1 is 2. 2 plus 2 is 4. So 4 on either side. For the next equation that we're doing, this is the oxidation of iron to iron oxide or rust. OK, so I would start this by just saying, OK, how many irons are there on either side? How many irons are there on the reactant side?
1.
Very good, 1. How many irons are in the products? 2. Very good. So what would I have to put in front of the iron in the reactants to make it balanced in iron? Yeah, I'd put 2, right? Because there's 2 irons on that side to make it balanced on the other side. So what? Whoa. I guess I did oxygens first. So let's keep going my way because I'm curious what's going to happen. Maybe I'll mess this up pretty badly. So the irons would be currently balanced. What about the O2 and the O3s? So we'd have a 2 here. So it's kind of weird, right? Like there's 3 oxygens here, there's 2 oxygens here. So to get these things balanced, you're going to have to multiply both of them at the same time. Because I mean, it's not like I can throw a number, like a nice whole number in front of O2 and make it 3. I'd have to put like 1.5 in front of 2. So what I'll do is I'll kind of do cross multiplication or crisscross, or multiply that by 2 to get 6 oxygens over there in the products, and multiply that one by 3, so it'll also give you 6. So I'm kind of like, OK, if I can't multiply one of them by a number, what if I multiply both of them by numbers? And OK, I know that I can at least make them 6 and 6. So let's do that. So 3 times 2 is 6, so 6 O's over here, and 2 times 3 is 6, so 6 O's over there. And that's balanced in oxygen. What about the iron? Well, I put a 2 in front of here, but that's not enough anymore because there's 2 times 2 irons. So that's 4 irons. And that means I put a 4 in front of that iron. Yeah, so I guess there's something interesting here. That if you do this correctly, like you don't really have to get it 100% right. What I mean by that is, like, if I multiply by too big of a number, or if I start in the wrong element, I won't have to get this perfect. If I ended up like going crazy and like multiplying by too big of a number, like let's say I went and multiplied instead of like, I'm like, oh man, I don't know that 6 is a multiple of 2 and 3. What if I said that instead of that, 12? What if I multiply it by 12? If that was the case, like if I had a 6 in front of the O2 and a 4 in front of the iron 2, iron 3 oxide, but it's iron oxide. If I had a bigger multiple of these numbers in front of it, I would notice that at the end, and then I would reduce it. So if somehow I managed to get 8 and 6 and 4 is the stoichiometric coefficients by kind of doing things and not paying attention to what the lowest common multiple of 2 and 3 was, it's still fixable because you'd notice, okay, well this does balance it, and these are all multiples of 2, so I can divide everything by 2. So that's 4, 3, 2 again. So the correct answer, the one that you want to put on a test, and there will probably be false answers occasionally to test this concept, is not only one that balances the equation, but it has to be the lowest whole number ratio, the lowest whole number set of coefficients that makes it work and makes it balanced. There are an infinite number of coefficients that do balance it, but you want to have the lowest whole number one so that we're all on the same page and you get the full credit. Yeah, so for example, if you had an equation where at the end you got 4, 2, and 4, that's totally cool. Just divide it by 2 to get 2, 1, and 2. So if you balance things element by element and you go a little too far, but it's still balanced, that's fine. You can fix it. Totally fixable.